Buenos días, ¿cómo están todos? Muchas gracias por haber retornado al segundo día de nada menos que UruComm 2021. Tenemos el placer de contar con Thiago Alves y Taufik Abrão de la Universidad Estatal de Londrina sobre el tema eficiencia espectral y eficiencia energética en Massive Multiple Input, Multiple Output y Non-Orthogonal Multiple Access. Cuando quieran, adelante.
My name is Thiago, and I am PhD student in the State University of Londrina, Brazil. And this paper has two authors, and the other is Professor Dr. Taufik Abrão. This presentation is organized in 5 sections: introduction, the system model, the spectral efficiency and energy efficiency, and numerical results, and the conclusion. Okay, the introduction. And my paper is on spectral efficiency and energy efficiency in massive MIMO and NOMA systems. NOMA and massive MIMO are the multiple access technique. They are currently attracting the attention of the research in wireless communication. And the NOMA is the no-orthogonal multiple access system, where the users are superposed in the power domain and separated the signals it's necessary in the receiver, and make use the successive interference cancellation, the SIC. The massive MIMO is a massive multiple in and multiple access technique. Is a method for multiplying the capacity of the radio link using the multiple transmission and receiver antennas, exploit the multipath propagation. And we propose compare the system performance on the 3 power location methods. This analysis involves on the system, on the spectral efficiency and the energy efficiency trade-off by determining the region of load and device trade-off for each system, and make use the area under the curve of the spectral efficiency and energy efficiency of each system. We find the more bit per antennas and bit per antennas per watt efficiency. And the system model, let's consider a multiple user single cell downlink transmission operating in a time division duplex with K single antennas active devices communicating with one base station, which is in the center of the cell, and equipped with M transmit antennas in now lateral side. In 3 configurations of antennas in BS, 64, 128, and 256. In NOMA, the system device are divided in 2 subsets, the KH and KL subset. The KH subset is formed by cell-center devices in the figure in yellow color, and these devices are located near to the BS. And the KL set, formed by the cell edge device in blue color in the figure, these devices are far from the BS. The channel model. The channel vector of device K is composed by the beta, is the path loss, and the H, the small fading. The path loss of device in KH subset is higher of the path loss of device in KL subset. To capture the effect of the physical radio, we consider the standard power law described in the equation 3 in dB, and dk is the Euclidean distance between the device K and the BS, and xc is the path loss attenuation factor. In addition, we consider a Haled flat fading environment where the channel power gains H are exponentially distributed in an IDD random variable with the unit mean like in equation 4. the transmitted signal in equation 5 and the received signal in equation 6, composed by the signal of interest and the interference signal. To get the data rates with zero force precoding, we use the equation 7 for the NOMA system and the equation 8 for the massive MIMO. In equation 7, the bar M is the again, the Heigen in NOMA system, and the M minus K, the Heigen in massive MIMO system. The tau is the part of current interval available for data transmission. The simulation took place in 3 stages. At each stage, the number of antennas in BH was increased. For each M, the number of devices grew from 2 until 2 times M. Okay, to obtain the energy efficiency, we divided the active data rate by the power consumption in watts, like in equation 9. The power consumption was calculated according to the equation 10, where are 5 portions. The first portion have the power frequency, considering the efficiency of the power amplifier, a fixed portion, consumption portion, and a dependent portion of the K, or the number of active device, a dependent portion of M, the antennas in BS, and the last one is the portion dependent, the K and the M together in watts. The power allocation strategies by devices applied in the paper is the equal power allocation, the classical water filling, and a modification in the classical water filling to serve the NOMA system. The classic water filling, unpairing the NOMA devices. To solve this problem, we propose a modification in classical water filling when the power are distributed with the difference of between the path loss into the pair. This is a table of simulation parameters. It's important to highlight here in the cluster I have 2 users. I have the time coherence, the coherence time interval is 5012, and I have the values of parameters in the energy efficiency analysis. And the path losses point is 3.78. In all the simulations is a Monte Carlo realizations, it's 1000. Now I show the numerical results. The first part of the figure, when the number of antennas in base station is 64, the trade-off between the spectral efficiency and the energy efficiency is achieved in the equal power allocation when the loading device is 0.875. In the second, when the number of the antennas in base station is 128, the NOMA achieve the best results, best trade-off with equal power allocation. And the device's loading is 0.734. In the last part in the figure, when the number of antennas in base station is 256, the trade-off between spectral efficiency and energy efficiency is achieved in modified water filling power allocation when device loading is 0.1594. Another metric and we use is the area on the curve, or the integral of the curve of spectral efficiency and the energy efficiency, divided by the number of antennas in base station. And this result about this is bits per antennas and bits per antennas per watts metric.
Thiago,
Okay.
temos 5 minutinhos mais, ok?
Okay. So in the finish. In summary, the best relationship between NOMA and massive MIMO system in bits per antennas occur in equal power allocation when the antennas in base stations is like 64 in the first graphic. In the second, the bits per antennas per watts, and the best relationship with NOMA with the massive MIMO system is follow the same tendency. To conclusion of the presentation, under the energy efficiency perspective, the massive MIMO achieved better results with employed the equal power allocation and water filling power allocation methods under K less than M. However, the NOMA can operate under high system loading, the K less than 2 times M minus 1. From the perspective of spectral efficiency and energy efficient trade-off, the NOMA attains superior trade-offs for all sets of the system configurations, achieve the highest device loading in all M configuration setups. In spectral efficiency analysis, the NOMA achieved the highest ratio, 2.76, when the antennas in base station is 64. The energy efficiency analysis, when the number of antennas in base station is 256, attain 1.8 ratio. These results corroborate the NOMA ability to operate suitable with high loading in 2 times number of antennas in BS. Thank you for your attention.
Muito obrigado, Thiago. Não temos perguntas. Se você tem endereço de e-mail, a gente pode enviar um e-mail.
Ok.
Muito obrigado.
Thank you.
Parabéns para vocês.